All right, this video is going to talk about the number of ways in which we can count things. It's a kind of an addition to the fundamental counting principle, only this time we're going to talk about large numbers, large possibilities. So like let's say, speaking of larges, you're ordering a pizza. You've got 4 toppings to pick from. How many different possible pizzas could you order if the pizza joint has 4 different toppings to pick from? And mathematically, we'd say that how many subsets of things could we have if we have 4 things to pick from, A, B, C, and D? Well, kind of thinking simply, well, what if we don't pick any of them, right? We technically could still have a cheese pizza, right? Or just a regular pizza. So there's one way, right, in which that can happen, very simply. We could also pick all 4 things. So again, there's one way to have a 4-topping pizza, right? They're all on there. But it's not any different if we order, A, B, C, D versus A, D, B, C, right? If we put the pepperoni on before the sausage before the pepperoni, it's still a sausage and pepperoni pizza. So again, there's one way, right? They're either on there or they're not. One way to do that. Again, if we think about 1-topping pizzas, we could either pick A, B, C, or D. So there's 4 ways to do that. If we pick 3-topping pizzas, I kind of like to think about that other side of things. Well, we could leave off A, B, C, or D, right? We could do A, B, C or A, B, D. But again, we could leave off any one of the toppings. So there's technically 4 3-topping pizzas that can be made. And if we pair up the letters, well, we can do A, B, C, and D. Or we could do B with C or B with D or possibly C with D. You'll find out there's 6 ways to do that. Now you may recognize those numbers. You may be familiar with the Pascal's triangle. That's actually row 4 of the Pascal's triangle, right? Or n equals 4 anyway. But basically these come from what we call combinations, right? 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. There are 16 total ways, right, if we add them all up, right, that can happen. Because again, it has to do with choosing when order doesn't matter. Now, you also could have shortcutted that. Again, the idea was, do we use A or do we not use A, B or not B? So you could also say there's 2 choices for each one of them. Take that to the 4th power, right? Because there's yes or a no question 4 times over. So again, 2 to the 4th would also get you 16. Kind of another way to think of that fundamental counting principle. But the big idea today is we're talking about, big numbers, and how we can kind of work with those. Combinations are a way of counting the number of ways n distinct objects can be chosen, r at a time. Right? So if we're looking at this and saying, well, 8 students wish to select a subcommittee of 4 to talk to the president of a college about tuition costs. In how many ways can the subcommittee be formed? Well, technically what we're saying is there are 8 students, right? And we're going to choose, right? We're going to choose a subcommittee of 4 of those students. But all that really matters is, are you on or are you off? If you're the 1st student on the committee versus the 4th student on the committee, you're still on that subcommittee, right? So again, the order in which you're chosen doesn't really matter. It just matters, are you there or are you not? So again, we would call that 8 factorial on the top over r, which is 4 factorial on the bottom. And then we always say 8 minus 4, right, or n minus r. 8 minus 4 would be another 4 factorial on the bottom. And again, we can work that out by hand, or we can hop onto our calculator, right, and we could type those in if you know how to type that into a calculator. And tell you what, let's go ahead and turn that calculator on for you. So give me 1 second, that'll pop right up. Meanwhile, you can always read that second question there. While I'm turning on this calculator, what we can do is hop on there and say, all right, we want 8. And if we go into our math menu, over to probability, notice NCR is our 3rd option. And then I can type in 4 and press enter. And again, if your calculator doesn't look exactly like that, don't worry, it's going to be the same general idea. You're typing in your n value, your total value first, 8. And then we want to type in our 4 after the combination, right? So again, our answer there is there's going to be 70 total ways. Oops, let's get rid of that big line there. 70 total ways we can make that happen. Same idea down at the bottom. Again, a standard poker deck of cards. We're going to deal 5 cards out. It doesn't really matter if you're the first card dealt or the 5th card dealt, right? If it's in the hand, it's in the hand. So what we're saying is, well, there's 52 cards, and we're going to choose to deal out 5 of them, right? Therefore, that's 52 over, again, 5 factorial, and then 52 minus 5, essentially 47 factorial. Again, you can work those out by hand or kind of narrow that down if you want to. But personally, I would just hop onto the calculator again and say 52 math probability NCR, right? And we're choosing 5 of them. And there are 2,598,960. 2,598,960 possible poker hands that can be dealt. Again, combinations are very helpful when order doesn't matter. The objects are distinct, but again, the order in which we're doing those things doesn't matter. It doesn't matter if you're the first card in or the last card in. If you're one of the cards in the hand, right, it works. Now, if order did matter, we're talking about what's called a permutation. So this would be more like the question down here. In how many ways can 3 competitors be chosen from a field of 8 to win the gold, the silver, and the bronze? Now, there's a difference between those, the gold, the silver, and the bronze, right? So what we want to say now, right, what we want to do now is go ahead and say, well, we're going to choose of the 8 possible people, right? We're going to permute. We're going to pick 3 of them, but the order matters, right? The order matters. Or if we really think about it, there are 8 people that can win gold, but then there's only 7 that can win silver, and there's only 6 that can win bronze, right? So the way this permutation works is we say 8 factorial divided by 8 minus 3, so we're just doing that subtraction. Notice we don't have the other 3 factorial on the bottom. So now it very simply came out to 8, 7, 6, 5 factorial, but over 5 factorial, which means those cancel. And like we said, we just get that 8 times 7 times 6. Or, again, we could hop onto our calculator. Again, type in 8, math. You may have noticed on that probability menu right above combinations was NPR, permutations. And again, we can choose 3 people. And it looks like we're 336 possible. 336 possible outcomes there. Again, when order matters, so such as the problem down here at the bottom, where we have 12 members on a campus botany club, we're going to select 4 candidates to be the president, the vice president, the secretary, the treasurer. They have different jobs. They have distinct different jobs, right? Well, in that case, of the 12, we're going to pick 4 of them. And again, very simply, I would just hop on here, 12, math, permutation, because order matters who's getting picked for what job. And we have 11,880. Possible ways to pick that slate of candidates, right? Again, when order matters, we call that a permutation. Now, a very distinguishable type of permutation, literally, is a distinguishable permutation. What if we're counting the order in which we can order letters, but we also have to care about repeated elements? So think about the words down here at the bottom. We've got the word folk, right? F-A-L-K. Well, we've got 4 different distinct letters, which means basically we've got 4 letters to pick from, and we're going to pick all 4 of them, which again essentially comes down to 4 factorial over 4 minus 4, or 0 factorial, and 4 factorial over 1 is basically 24 possible ways that can happen. Well, in the middle word here, now we've got 7 letters. So we've got 7 factorial possible ways this can work. But now careful, if we switch the A's around, right, we wouldn't know the difference. We're not going to know that that's a different order of letters. We don't know it's not like there's a blue one and a red one, right? If we switch the A's, we wouldn't know it. So what we need to do is say, well, if I switch the A's, that's not a new order. It doesn't look different, right? It's not distinguishable. It doesn't look any different. So I need to divide away the number of ways in which I can switch those A's around. Well, I can switch the A's. I can either write them as sort of like we said, if they were 2 different colors, the red then the blue, or the blue then the red. Or basically there's 2 factorial ways to reorganize the A's. So it's not just 7 factorial, right, which would be equal to, give me one second here. which would be equal to 5,040 possible ways to organize 7 things. Now we got to cut that in half, right? Purely because every time we switch the A's, we wouldn't know the difference. Well, let's do the same thing over here. We've got 6 letters, so 6 factorial. F is only in there once, so technically you could say divided by 1 factorial, but we've got 2 E's and we have 3 R's. Well, the number of ways we can reorganize the R's then is 3 factorial ways to do that. So again, we've got 6, 5, 4, 3, 2, and 1 over 2 times, again, 3, 2, and 1. Cancel those away, cut that 4 in half maybe, and 30 times 2, there are going to be 60 total ways, right, to reorganize those letters. That's a distinguishable permutation. The number of letters on the top, factorial, right, all the ways we can order those, but then we have to divide away all the ways that we can't tell the difference, right? If we start switching letters and we don't know the difference, those are repeated elements, then we've got to divide away those options. They're not distinguishable. They're not different from the original. All right, a couple other quick examples just where we can use these combinations and permutations, what you want to kind of think through. What if we were running a 7-horse race, right, an invitational horse race? Zach claims he can predict the finishing order of the top 3 horses, the win, the place, and the trifecta. How many different ways can the top 3 horses finish? Well, again, we're predicting the win, the place, and the show, right? The win, the place, and the show. We care about the order. So therefore, we're saying 7 permute 3, right? And again, you could always go find that number pretty quickly and easily. Samantha doesn't think she can think up the order, but she thinks she knows which 3 will finish on top. Well, now if the order doesn't matter, just who's going to finish in the money, right? You could be 1, you could be 3, but as long as it's those 3 horses, we're not caring about the order in which we pick them. Now we're going to say that's a 7C3, right? That's a combination. So hopefully that helps you kind of distinguish between those 2 different ideas. If the order matters, there's a difference between 1, 2, and 3, right? When we pick them, horses ABC versus ABD or even CAB, right? If the order is different, then it's a permutation. If all that matters is a grouping of horses, that's a combination, very simply. One last one for you here very quickly. Marshall knows it's Mother's Day is coming up and goes to buy a bouquet containing 4 flowers. 2 of the flowers are to be daisies and 2 are to be carnations. Jocelyn the florist has 8 daisies and 5 carnations in stock. How many ways can they choose the flowers to fill that order? Well, realize we've got 8 daisies to pick from. And again, we're not going to really care about the order in which we pick them, so let's just call it a combination. But we're going to choose, right, 2 daisies of those 8 daisies. And at the same time, from the 5 carnations, we're also going to choose, right, 2 of those flowers. So realize if we want to do both of those things at the same time, we're doing one and the other, right? Basically, we're just going to multiply. Right? So very simply, 8 choose 2. So let's hop on our calculator there. Again, 8 math, probability, choose 2. And then we're going to multiply that by, right, 5 choose 2. So over to probability, and again, 3. And we're going to choose 2 of those. So we need to take 28 times 10, or basically there are 280 possible flower orders we can have. Right? Thomas comes to buy flowers, but he could do 1 rose and 3 lilies, 3 roses, 1 lily. He's not sure the difference here if you read through that question. And we've got 12 roses to pick from and 4 lilies. Well, how can we fill that order? Well, what if we chose, of the 12 roses, right, we're going to choose 1 of those. And at the same time, right, we've got to choose from the 4 lilies. We're going to choose 3 of them. But wait a minute, since Thomas doesn't know which order he wants, we could also, from the 12 roses, choose 3, and the 4 lilies, choose 1. Again, that addition there is basically because we're saying we could be one or the other. One or the other. So again, and when you're doing 2 things at the same time, we're doing 1 set of flowers and the other, we multiply. But or typically means we're going to add. I'm going to let you go and find those letters. If you have any questions, though, feel free to ask your teacher. Otherwise, have a great day.